Good morning, everyone. We are from ComSats, University Islamabad, WA Campus, Department of Electrical and Computer Engineering. Today, we are excited to present our project titled AI-Based Weather Prediction. I am Yashara Idris, and my fellow group member is Nabila Niazi. Our project supervisor is Sir Muhammad Ali, who has provided us with invaluable guidance and support throughout this project. Imagine you are a farmer whose crops are ready to grow, and you checked the weather prediction on your mobile, and it shows that it will be sunny in your city. But suddenly it started raining heavily in your neighborhood. The unexpected downpour could damage the plants, and you're unsure if the drainage will hold up. Presenting an AI-based weather prediction system that provides accurate, localized forecasts to help you make informed decisions. We place our sensor network in the fields, where it collects readings of temperature, humidity, and air pressure, key parameters for weather prediction. This data is then sent to an AI server using radio frequency communication. In our case, the AI server is a Raspberry Pi 4 equipped with a radio frequency receiver, which receives the sensor data, performs all the AI processing, and then sends the predictions to a central server. In this presentation, we will walk you through how artificial intelligence can be leveraged to predict weather patterns more accurately and efficiently. Imagine needing real-time weather updates for your specific location, but relying on a system built for regional forecasts. Despite advancements in technology, traditional weather forecasting still faces significant limitations. Some of them include traditional weather forecasting systems often lack the precision needed for localized, real-time insights. Conventional weather stations are costly, complex, and inaccessible for small-scale or individual users. There is a growing need for an affordable, scalable, and real-time solution for localized weather monitoring. After identifying the limitations of traditional weather forecasting, we were motivated to work toward a better solution. Our motivation can be summarized in the following key points: growing reliance on weather data for agriculture, disaster management, and daily planning, lack of affordable, accessible, and real-time weather monitoring systems for local environments, the potential of IoT and AI technologies to revolutionize traditional weather forecasting, desire to create a practical solution that empowers users with accurate, localized, and predictive weather insights. Collect temperature, humidity, and air pressure data using sensors and Arduino Nano. Transmit data wirelessly using nRF24L01 Plus modules to Raspberry Pi. Upload real-time data to Firebase Real-Time Database. Apply regression models for weather prediction. Use classification models to categorize weather conditions. Log real-time data for improving future AI model training. Develop a website to display weather data using HTML, CSS, JavaScript, and chart.js. On the sending side of our system, we have integrated two key sensors, the DHT11 and the BMP180. The DHT11 sensor is responsible for measuring temperature and humidity levels, providing essential environmental data. Meanwhile, the BMP180 sensor is used for the accurate measurement of atmospheric pressure. Together, these sensors allow us to collect comprehensive weather parameters for further processing and prediction. An Arduino Nano is used to collect data from all the connected sensors. It processes the raw data into a suitable format for transmission and then sends it to the nRF24L01 Plus wireless communication module for further transmission to the receiver side. Now let's look at the block diagram for the receiver side of our system. We begin with the nRF24L01 Plus receiver module, which is responsible for receiving environmental parameters like temperature, humidity, and air pressure sent from the sender side. The received data is then passed to the Raspberry Pi. The Raspberry Pi acts as the central processing unit that handles incoming data. From here, three major paths occur simultaneously. First, the data is fed into a classification algorithm to categorize the type of data or condition we are dealing with. Secondly, it is used in machine learning algorithms for prediction, helping us forecast or predict future outcomes based on the patterns in the data. And the Raspberry Pi saves the data locally as an Excel file containing new data, which is stored in Firestore, another storage solution that supports easy retrieval and analysis later on. After processing, the results are sent to Firebase, a cloud database, for real-time storage and synchronization. Finally, the processed and stored information is displayed on the website, allowing users to easily view and interact with the results. This entire flow ensures we have a smooth pipeline from data reception, processing, prediction, storage, and visualization. On the sending side, we have a setup consisting of multiple sensors and an RF transmitter. First, there is the DHT11 sensor, responsible for measuring atmospheric temperature and humidity. Next, we have the BMP180 sensor, which accurately measures atmospheric pressure. An Arduino Nano acts as the central controller, collecting the readings from both sensors, processing the data, and transmitting it to the receiving side using an NRF24L01 plus RF module. This is the receiver side. It is relatively simple, consisting of an Arduino Nano and an NRF24L01 plus module, which receives the transmitted data from the sending side and decodes it for further processing. The decoded data is then sent to a Raspberry Pi 4, where it is received, stored in an Excel file, and processed further. The Pi also runs machine learning algorithms for prediction and classification tasks, enabling advanced data analysis and decision-making. This is the sending side, which is sending data using NRF. This is the receiving side, where data is received via the NRF module and transmitted to the Raspberry Pi. As shown on the screen, we can observe that the data is being successfully received and processed in real time. This is the website that displays the current and predicted values of temperature, humidity, and air pressure. As shown, we can view the predicted values for up to 4 days, offering insight. In conclusion, developed a low-cost, real-time smart weather station using IoT-integrated wireless data transmission, NRF24L01 Plus to Raspberry Pi, real-time monitoring and cloud storage via Firebase, applied machine learning for accurate weather prediction, useful for agriculture, disaster management, and daily planning, scalable and adaptable for various environments.